on the motion of particles under simple harmonic motion, and what we are going to do in this lecture is forced damped harmonic oscillator. And let me explain what that means. You have earlier learnt about damped harmonic oscillator, and that was described by an equation x double dot plus bx dot plus kx equal to 0, which translated to x double dot plus gamma x dot plus omega 0 square x equals to 0. And the solution of this was x t equals some amplitude that decayed with time, cosine or sine omega 0 t. Here gamma is b over m and omega 0 square is k over m. So, what happens in this oscillator is as time progresses, its amplitude keeps going down, and a general solution as a function of time, if shown graphically, looks something like this. So, this is x t. It goes down with time exponentially. This is kind of this is exponentially going down. This green curve is e raised to minus gamma by 2 t, and inside there are oscillations of omega 0. So, this is damped harmonic oscillator. You also learnt about forced free oscillator, or what I will call is forced undamped oscillator. And what I mean by that is, this was an oscillator where we had applied a force of the form f cosine or sine omega t to the oscillator, this is k x, so that we had x double dot plus omega 0 x equals f over m cosine of omega t. And you saw in this that x as a function of t was a combination of the original or homogeneous part of the equation. That means, this part belongs to, let me write it on the right upper screen, x double dot plus omega 0 x equals 0. This was a solution of that, and there was a particular solution which was given by m f over m omega 0 square minus omega square cosine of omega t. So, these are the two oscillators we have studied. What we want to do now is study forced and damped. So, this oscillator is forced, that means I am applying a periodic force of the kind f cosine omega t, and it is also damped oscillator. And most of the oscillators you see around you are of this kind. For example, you take a swing in the park, or the pendulum in clocks. If left unattended, that means if I take a swing and leave it, with time it slowly comes to equilibrium, the amplitude keeps going down. Similarly, in the pendulum you need a battery to keep it going. And the battery is needed because of the damping, the energy keeps going down, as we just saw, the amplitude keeps going down, and to compensate this loss, I have to supply energy from the outside. Swing in the park, you always push it, every time you push it, and therefore, that makes it maintain its amplitude. In pendulum in clocks, the energy is supplied by the battery. Of the old clocks, it used to be supplied by springs. So, now we want to study this oscillator, and let us see what does the equation look like. So, again if I write the equation, there is a mass which is accelerating and it is going under the force minus Bx dot, that is there is a force which is drag force acting against its velocity minus the restoring force and plus I have applied a force F cosine of omega t. Omega is not equal to omega 0. By now you understand what omega 0 is. And this equation can be transformed to x double dot plus gamma x dot plus omega 0 x equals F cosine of omega t. That is the equation for forced damped harmonic oscillator, and we need to find the solution for this. Recall from forced undamped oscillator that the motion was a combination of two different frequencies. One was omega 0 and omega, that is the natural frequency of the oscillator and the frequency with which we are applying the force. And at omega equals omega 0, the amplitude of the oscillator grows linearly with time, right. So, if the frequency of the applied force becomes the same as the natural frequency of the oscillator, then the amplitude grows with time linearly and finally becoming very large, and this is known as resonance. Can something similar happen in damped harmonic oscillator when they are forced? Does it still happen that the motion is a combination of two different frequencies, one a natural frequency and one the frequency with which the force is varying, and two, does the amplitude go to infinity? So, this is what we are going to explore in this lecture. Again, all the answers are given by solving the equation. So, the answers are provided by solving the equation of motion, and I will keep appealing to the solution for undamped harmonic oscillator. So, let me write on the left what happened in undamped oscillator. The equation there was x double dot plus omega 0 square x equals F over m cosine of omega t, and the solution was solution of the homogeneous equation, and that means A cosine of omega 0 t plus B sine of omega 0 t plus a particular solution which was F over m omega 0 square minus omega square cosine of omega t. Now, let us see what happens in the damped oscillator. In a damped oscillator, the equation is x double dot plus gamma x dot plus omega 0 square x equals F over m cosine of omega t. And as is the case in undamped oscillator, the solution is a combination or mathematically the correct term is superposition of two different solutions. One is the homogeneous solution. So, x t is going to be the solution of the homogeneous equation, which we have already learnt is of the form e raised to minus gamma by 2 t. And let me now write cosine of omega 0 t plus b e raised to minus gamma by 2 t sine of omega 0 t plus x particular. And x particular is going to depend on the applied force. If the applied force is 0, there is going to be no x particular. But why I wrote this solution in this particular way is because see what happens to the first term, which I am putting in the box as time progresses. So, the equation that we are solving is x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t, and the solution I have written is a linear combination or superposition of two different solutions, which is e raised to minus gamma by 2 t a cosine of omega 0 t plus b e raised to minus gamma by 2 t sine of omega 0 t plus x particular. Recall that x particular was f over m omega 0 square minus omega square cosine omega t in the case of undamped oscillator. Now, as time progresses, as t becomes large, that means suppose you are in a park, somebody is sitting on a swing and you are starting it by applying a force. Initially this solution is going to be there, but as time progresses the solution a e raised to minus gamma by 2 t cosine omega 0 t plus b e raised to minus gamma by 2 t sine omega 0 t is going to go to 0. This solution just dies down, and what you are left with is you are left with x particular t equals the solution x t. So, finally, the pendulum or the oscillator is going to oscillate with the solution given by x particular. The homogeneous solution dies down, and that is what we are interested in. What is the final motion? So, this we are interested in this motion. The other one has died down, right. So, initially there may be the combination of two frequencies omega 0 and omega, but with time the omega 0 solution dies down, and in technical terms these are known as transient solutions. Right, these are transient, that means they come for some time and then they die down, all right, and this is what is known as steady state solution. So, we are interested in this motion, means we are interested in the steady state solution, and that is what we are going to focus on. If somebody asks you why are you neglecting the first term, and you can always say it is a damped oscillator, its natural motion with omega 0 frequency always dies down with time, and finally what we are left with is the steady state solution. So, from next slide on I am going to now focus on steady state solution. So, steady state solution for a forced damped harmonic oscillator. And by that what we mean is that the solution, so let us understand that the solution e raised to minus gamma by 2 t a cosine omega 0 t plus b e raised to minus gamma by 2 t sine of omega 0 t has gone to 0, right. So, let us write this transient solutions have died down and we are left with only the steady state solution, and by solution means this is the kind of motion I am going to now observe. And let us see what does it look like. So, my equation is x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t. So, recall in undamped oscillator what I had done, where the equation was x double dot plus omega 0 square x equals f over m cosine omega t, we had assumed a solution of the form x t equals some amplitude cosine of omega t. That means, we had assumed a solution of the same frequency as the applied force. Does the same trick work here? So, let us analyze that. So, now we are looking at x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t, and we want to try the solution of the form x t equals some amplitude a cosine of omega t. Does this work? Let us see. The best way to look at it is to substitute this. So, substitute this in the equation of motion. So, x double dot or x dot t is minus omega a sine omega t, x double dot t is minus omega square a cosine of omega t, and we substitute this in the equation. I get minus omega square a cosine omega t plus gamma times minus omega a sine of omega t plus omega 0 square cosine of omega t equals f over m cosine of omega t. So, left hand side contains both cosine omega t and sine omega t. On the other hand, right hand side contains only cosine omega t. So, this equation cannot be satisfied with this kind of solution. What do we do? Let us see that. So, I started with x double dot plus gamma x dot plus omega 0 square x equals f over m cosine of omega t, and when I took the solution x t equals a cosine of omega t, I got on the left hand side terms containing both cosine omega t and sine omega t. On the other hand, right hand side has only cosine of omega t. So, what the best trick is to generate some terms that will also give you more sin omega t on the left hand side, so that I can cancel this term. So, what we do now is therefore, take the solution, take x t of the form a cosine of omega t plus b sin of omega t. What we will hope to do with this is that on the left hand side, I will equate the terms that appear with cosine omega t to the right hand side equals f over m, and those containing sin omega t I will equate to 0. So, let us do that. So, x dot t is going to be minus omega a sin of omega t plus omega b cosine of omega t, and x double dot t is going to be minus omega square a cosine of omega t minus omega square b sin of omega t. And when we substitute that in the equation, I am going to get minus omega square a plus omega b plus omega 0 square a cosine of omega t, and for the sin omega t terms I am going to get minus omega square b minus omega a plus omega naught square b sin of omega t. These two terms are to be added, and this together added together should be equal to f over m cosine of omega t. Now, you see I have two variables a and b, and I will get two equations. By equating the terms of cosine omega t, I get one equation which says that a combination of a and b equals f over m, and from the second equation I get a combination of a and b equals 0. So, let us do that now. So, I am getting minus omega square a plus omega, let us see, there should be a gamma also somewhere, because I missed that. So, let me correct that. The term with omega x dot term also had a gamma. So, I am correcting that here. So, there is a gamma term. So, minus omega square a plus gamma omega b plus omega naught square a equals f over m. And the second equation says minus omega square b minus gamma omega a plus omega 0 square b equals 0. Two equations and two unknowns. So, now I can solve them from the second equation. So, let me label them. This is my second equation, this is my first equation. From the second equation, I get b equals gamma omega over omega naught square minus omega square a. And I substitute this in the first equation, right. So, substitute equation 1, and I am going to get minus omega square a plus omega naught square a and plus gamma square omega square over omega 0 square minus omega square a equals f over m. So, I get a omega 0 square minus omega square plus gamma square omega square over omega 0 square minus omega square equals f over m. I have found the value of A. Let us write that explicitly. So, I get A equals omega 0 square minus omega square over omega 0 square minus omega square square plus gamma square omega square f over m. And what was B? This was my B. So, B was gamma omega over omega 0 square minus omega square times A. So, this comes out to be gamma omega over omega 0 square minus omega square square plus gamma square omega square f over m. Now, I have found both A and B, and therefore, I can write my steady state solution as x t equals omega 0 square minus omega square over omega 0 square minus omega square square plus gamma square omega square cosine of omega t plus gamma omega over omega 0 square minus omega square plus gamma square omega square sine of omega t, and this whole thing is multiplied by f over m. That is my steady state solution. So, it contains both cosine omega t and sine omega t. The question that we now ask is, what is the amplitude of this motion and how does it look compared to f cosine of omega t. Let us see that. I am again going to write this x t is omega 0 square minus omega square divided by omega 0 square minus omega square plus gamma square omega square f over m cosine of omega t plus gamma omega over omega 0 square minus omega square plus gamma square omega square f over m sine of omega t. So, I know this motion is periodic. Let us observe that, right. Number 1, x t is periodic, and it is periodic with the same frequency, that is omega as the frequency of the applied force, right. However, it contains both cosine omega t and sine omega t terms. So, it cannot be right on top of f. Let me explain what does that mean. So, if I were to plot f t versus time, it will look like a cosine omega t curve, right. So, this is f t, this is time, and f t looks like this. On the other hand, the steady state solution has both cosine omega t and sine omega t, and therefore, is going to look different, although same frequency, but it is going to be shifted with respect to this. So, this is my x t. How exactly it is shifted? What is the amplitude? That is what we are going to find next. So, to find the amplitude of motion, and I am going to introduce one more term, the phase of motion, that means phase with respect to the applied force, how much it is shifted with respect to applied force. We do the following trick. We have x t equals omega 0 square minus omega square over omega 0 square minus omega square square plus gamma square omega square f over m cosine of omega t plus gamma omega over omega 0 square minus omega square square plus gamma square omega square f over m sine of omega t. I want to write again in terms of cosine omega t, so that I see how much it is shifted with respect to cosine omega t curve. So, I am going to write omega 0 square minus omega square over omega 0 square minus omega square square plus gamma square omega square as 1 over square root of omega 0 square minus omega square square plus gamma square omega square times omega 0 square minus omega square over square root of omega 0 square minus omega square square plus gamma square omega square. Let me put this in brackets, and I am going to write gamma omega over omega 0 square minus omega square square plus gamma square omega square as 1 over again this square root of this quantity omega 0 square minus omega square square plus gamma square omega square in the brackets gamma omega over square root of omega 0 square minus omega square square plus gamma square omega square. Notice that the quantities in brackets, if I call this C1 and call this C2, notice that C1 magnitude is less than equal to 1, C2 magnitude is less than equal to 1, and C1 square plus C2 square is equal to 1. Right. So, I have C1 equals omega 0 square minus omega square over square root of omega 0 square minus omega square square plus gamma square omega square. Its modulus is less than equal to 1, and therefore, I am going to call C1 equals cosine of some phase phi. Phi is constant, is independent of time, and similarly C2 is equal to mod C2 is gamma omega over square root of omega 0 square minus omega square square plus gamma square omega square is also less than equal to 1, and I am going to call C2 sin phi. And I am justified in doing that because I have, as I pointed out in the previous slide, C1 square plus C2 square equals 1, that you can check very easily. And therefore, my steady state solution is x t equals f over m square root of omega 0 square minus omega square square plus gamma square omega square cosine of omega t cosine of phi plus sine of omega t sine of phi, which can be written as x t equals f over m square root of omega 0 square minus omega square square plus gamma square omega square cosine of omega t minus phi, where I can write cosine of phi is equal to omega 0 square minus omega square divided by square root of omega 0 square minus omega square plus gamma square omega square. Sine of phi is equal to gamma omega over square root of omega 0 square minus omega square square plus gamma square omega square. Sometimes this is also written in terms of tangent of phi tangent of phi is equal to gamma omega over omega 0 square minus omega square. But what is more important is that the steady state solution, the state solution lags behind the applied force. What does that mean? If applied force reaches certain value, say its maximum value at some time t, x would reach that value slightly later, because it is in omega t minus phi is catches up slightly later, right. So, it is lagging behind. That means, so if we were to plot f t versus t, this is t, this is f t, it follows a cosine curve. The x curve is such that it reaches later if wherever f is reached. So, f had a peak maximum value at t equal to 0, the x is going to have that value slightly later. So, that will start slightly later. So, it will be shifted. Although I have shown the amplitude roughly the same, the amplitude is going to be different. So, let me show you a slightly different amplitude. It is going to be something like, it will start maximum from here and then it is constantly shifted. So, this is like x t. It still has that cosine omega t behavior, but wherever f reaches, so f reaches a 0 value at this point, the x will reach here slightly later. Let me erase the red curve now, just to erase this, to remove the confusion. So, it lags behind, and this difference is phi divided by omega. So, it lags behind. Now, does the phenomena of resonance take place? So, I hope by now I have made it very clear that the steady state solution has the same frequency as the applied force. It has an amplitude, right. So, amplitude of f over m square root of omega 0 square minus omega square plus gamma square omega square. Phase, which is lagging behind, so minus gamma omega over square over omega 0 square minus omega square, and it lags behind, right, and same frequency as the applied force. So, it has the same frequency as applied force, has an amplitude that depends on the applied force. Naturally, more the force you apply, larger the amplitude, and it lags behind because of the drag. That makes sense, because whatever force you apply, the drag kind of makes it respond slightly later. So, it lags behind in the way it responds. Next question we ask is there resonance? So, the question we are asking is there a resonance? What does that mean? Does the amplitude go to a very large value for certain applied frequency? So, let us look at that. The amplitude in a steady state motion is given by f over m square root of omega 0 square minus omega square square plus gamma square omega square. It does appear that it will go to a very large value, right, for certain omega, because if omega 0 square minus omega square goes to a smaller and smaller value, the amplitude goes up. So, let us find that out. That we can find out by writing d by d omega equal to 0. that gives me maximum or minimum. In this case, it's going to be maximum, and you can check that by taking the second derivative. And this is going to come out, so dA by d omega is going to come out to be f over m is always there, 1/2 1 over omega 0 square minus omega square square plus gamma square omega square raised to 3/2, and on the top I am going to get times 2 omega 0 square minus omega square times minus 2 omega plus 2 gamma square omega. That is the numerator, divided by 1 if you like. And there is a minus sign, but we do not bother about that because this whole thing is to be made to be 0. And what that means is I am going to get 2 omega 0 square minus omega square times minus 2 omega plus 2 gamma square omega equal to 0. And that gives me the frequency omega at which the amplitude goes to a very large value. So, this gives me omega 0 square minus omega square minus 2 is equal to minus gamma square, or omega 0 square minus omega square equals gamma square by 2, omega square equals omega 0 square minus gamma square by 2, omega is equal to, I can take omega 0 out, 1 minus gamma square over 2 omega 0 square raised to 1/2, and for gamma much less than omega 0, I can write omega is roughly equal to omega 0 1 minus gamma square by 4 omega 0 square, which is omega 0 minus gamma square by 4 omega 0. Again, gamma is much less than omega 0, so this is roughly omega 0. So, the amplitude reaches a maximum at roughly omega equals omega 0. So, if I were to plot the amplitude as a function of frequency of applied force, and what does the amplitude look like? A omega is some constant f over m divided by square root of omega 0 minus omega square plus gamma square omega square. It looks like this. It reaches a maximum very close to here and then comes down. This is what it looks like. So, it reaches maximum near omega 0. So, this is the phenomena of resonance. What does that mean? That at, so this is the phenomena of resonance, that means at frequency omega very close to omega 0, the amplitude of steady state motion becomes large, and it takes a very large value. This is different from resonance in undamped oscillator, where we saw that when the frequency of applied force was equal to the natural frequency, the amplitude grew with time. It kept growing with time. Here it does not grow, it just takes a maximum value. There is a nice interpretation of resonance in terms of energy. You see, now what is happening is this oscillator is oscillating, right. So, power supplied by the force is going to be equal to F times V, all right, F times V. Now, x t is equal to some amplitude which we have already written, cosine of omega t minus phi. So, V t or the velocity of the oscillator is going to be minus omega a sine of omega t minus phi. So, the power is going to be equal to f v, which is equal to minus omega a. F is f cosine of omega t times sine of omega t minus phi, which I can write as minus omega a f, and I can write this as cosine of omega t sine of omega t cosine of phi minus cosine of omega t square sine of phi. That is the power. So, the power is equal to minus omega a f cosine omega t sine omega t cosine phi minus cosine square omega t sine phi. So, average power per cycle is going to be equal to this power, which is varying with time, integrated over time from 0 to the time period and do 1 over t. So, this is going to be equal to minus omega a f integration 0 to t cosine of omega t sine of omega t dt times cosine of phi minus 0 to t cosine square omega t sine of phi dt and 1 over t, where t is 2 pi over omega. You can easily show that 0 to t cosine omega t sine omega t dt is 0, integration 1 over t cosine square omega t dt is 1/2, and therefore, average power per cycle is plus omega a f sine of phi divided by 2. The sine of phi I am going to call the power factor. I will comment on it in a minute. So, average power is some omega a f by 2 sine of phi, and the average power is going to be maximum. This will be maximum when sine phi is maximum, because there is nothing else that can vary. Omega is a constant, a is kind of constant, right. So, I can write this as average power is omega, a was f over m square root of omega square minus omega 0 square plus gamma square omega square, and then there is one more f. So, this becomes f square sine phi. So, roughly I can say when sine phi is maximum, my power is going to be maximum. I am ignoring little variation of this omega here. So, sine phi maximum is 1, which implies phi equals pi by 2, which implies cosine phi equals 0, and that means omega 0 square minus omega square over square root, that whole thing is equal to 0, implies omega 0 square equals omega square, or omega 0 equals omega. So, what have we learnt? The average power supplied by us, or the average power supplied by us, is maximum when resonance occurs, right. So, that is the interpretation. So, let us conclude that average power supplied by us is maximum at resonance, and this also implies in a steady state motion the power supplied is equal to power dissipated. And that makes perfect sense, because if power supplied is equal to power dissipated, the amplitude is not going to change. So, the two are equal. So, we also conclude that at resonance, power dissipated by the system is maximum. Mind you, I am making these statements ignoring that gamma omega or 1 over omega naught square minus omega square kind of dependence precisely. So, it is going to be near omega 0, but you get the idea that sin phi being maximum gives me maximum power loss, dissipation, or maximum power supplied by us. And I said earlier that I am going to interpret that sin phi, which is power factor, a place which you are going to learn in your 12th grade, where this damped, force damped oscillations occur, is LCR circuit. So, let me just comment on that. So, in an LCR circuit, what we have is a resistance, an inductor and a capacitor, and this is connected to an AC supply. This AC supply is like your force which is driving the current. R resistance is like your damping system that actually takes away energy, and L and C provide the natural frequency. So, in this you will later learn that the power dissipated in the resistance is maximum when certain conditions are met, and that is precisely what gives you the power factor. That precisely what tells you when you are going to get maximum heat dissipation, right. So, this is just a comment on the side. So, to conclude these lectures on harmonic oscillator, in these 5 lectures what we have done is we have learned about periodic motion in general, then we learned about simple harmonic motion, where the equation satisfied was mx double dot equals minus kx. That means there was a restoring force proportional to the displacement, and this gave solutions of the kind A cosine omega t plus B sin omega t, where omega equals the square root of k by m. Then we also learned about the phenomena of resonance in forced undamped harmonic oscillators, and in this case we saw that the amplitude grows with time linearly like this. Then we introduced damping into the system, and we learned about friction, how that affects the motion, and we also learned about velocity dependent damping. In the second case, we learned that x t is given as a e raised to minus gamma by 2 t, and then that oscillatory term cosine omega t plus b e raised to minus gamma by 2 t sin omega t. And finally, we learned about forced damped harmonic oscillator in this lecture. From next lecture onwards, I am going to introduce the wave phenomena and see what waves do and how we can describe them. Thank you.